10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Woohoo! And happy Pi Day, everybody. We have a little better reason to be here than just a geeky New Year's Eve style countdown. I have a small talk I've been giving recently in honor of Pi Day, and I thought there'd be no better time to turn it into a screencast than right now. I've started this material for a class that I'm a TA for at Loudoun Valley High School. Great students. Hey, everybody. And in fact, that's why I'm wearing the t-shirt today. This is a Pi Day t-shirt that we had at school. And this started out just showing the students that they already know how to calculate pi. In fact, you do too. You know everything you need to do to be able to calculate pi. Now, I'm going to show you how to do that, but then we're also going to go into a little Pi Day geekery, and I'm going to show you a few different algorithms, some you'd never come up with on your own. I know I couldn't. But the first one we're going to look at is something that everybody should know how to do. If you know how to calculate the area of a circle, and if you can remember the Pythagorean theorem, and if you can generate random numbers, then you too can calculate the value of pi. Let's go into how that works. Okay, so first let's recap what pi is, right? If you remember your, I don't know, junior high, high school, something like that, we take a circle, and we take its diameter. And if we were to take that diameter and put it out along the edge of the circle, we get, about once, twice, 3 times, but there's this little gap left over, right? And that little gap, is about, 14% of that line. So we often call that value pi, and the value of pi is 3.14. At least that's pretty much what we all learn it as. Now, if you might remember that pi is one of these really funky transcendental, non-repeating, yada, yada, yada kind of numbers that if we actually were to try to calculate it out, 3.141592653, yada, 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 yada. And it never ends. No matter what we do, no matter how long we calculate, that number never ends. That's why today is Pi Day. It's March 14th, 2015. And it's a special Pi Day because this 15, that only happens once a century. And of course, right now, it's 9:26 in the morning and 53 seconds. So that's why today is Pi Day. Well, how could we ever calculate this ever-increasing number of pi? I mean, if I tried to do this with a ruler, I would need a more and more accurate ruler to get down to all these decimal places. In fact, if you look at the Wikipedia article on pi, it says if you know pi to 39 digits, that is enough to calculate the volume of the universe to within the accuracy of an atom. So yeah, that's 39 digits. Why would we ever need more than that? Now, that's it's a way of drag racing computers basically, but that's why we're going to play with it today. But how can we ever know that number any more accurately than we could with a ruler? Well, that's what we're going to talk about today. You might remember from your junior high, high school math how to calculate the area of a circle. Let's take another circle and its radius, which is just half of the diameter. So you can think of this as picking a center and sweeping out the radius to get the circle. Let's call that r. The area of that circle, that is, however much space that is, depends on that radius. And that is pi r squared. And to anyone who ever in high school math looked at this and said, why would I ever need to know how to do that? You know what? I use that in the real world to calculate the volume of my wedding cake when I was scaling up a recipe to serve 150 people. But that's a story for another time. If I've ever recorded my metrics talk, you can find it there. So if that is a radius 1, we kind of have a special case here. What does the area of that circle come out to be? The area of that circle comes out to pi 1 squared, which is of course 1. The area of that circle equals pi. Well, that's convenient. If we were to put a box around that circle, So the radius here is 1. We know that's 1. So we know that's 2. That's 2. The area of the circle is 2 times 2, or 4 unit squares, typically how we say that. If that were a foot, it would be 4 feet squared. So that's pi, which is 3.14 something, and that's 4, slightly larger. That makes sense, slightly larger because of these areas. Well, there's one more thing that I want to ask you here. And if I were to pick a random point on here, let's say here, and I would know, this value as, let's say, 0.4, and this value as 0.6, as if it were on a sheet of graph paper, what is this distance? Let's call that x, that y, and that z. And that should seem familiar to you too. That's called Pythagorean's theorem. And that z is, you often see this equation where z squared equals x squared plus y squared. Or z equals the square root of x squared plus y squared. So how is knowing that distance useful? Well, if we can compute that distance, we would know if I pick a random point, let's say there, I could tell if it's inside or outside of that circle. It's outside if that distance is greater than this radius. So let's zoom in now on just a quarter of that circle. So here's our box with the center of the circle and that first box we drew, or the second box we drew. And here is a quarter of our circle. So I'm going to pick a random point. Is that inside or outside the circle? That's inside. I mean, I can tell that visually, but the computer can figure that out because we know that distance. Is that inside or out? Outside? Outside? Well, on the line. Outside, inside, outside. If we were to do this 1,000 times, besides being a lot of math that I have to do by hand, we would get some value here. Let's say we did it 1,000 times. How many were inside the circle? Just call that, I don't know, I for now. Well, that looks like it's, I don't know what. That's, let's see. That is half, so it's more than half. Well, it's maybe a little less, a little more than a third. I don't know. If we were to just keep doing this, we know it's about a third, right? So it's about 75. So out of 1,000, we'd get about 750 in there. Maybe a little more, maybe a little less, because it's completely random points. But a really neat thing happens here. If we take that value, if we let the computer calculate that, and we multiply it by 4 to get the full circle back, well, what is inside the circle approaches the value of pi. Because, the chances of it landing inside the circle versus outside the circle are the same as, pi over the volume of the area, which here the volume, of the whole thing. Well, anyway, let's play with that on the computer with a little bit of math. So I'm sitting in front of my trusty text editor, and it's ready to interpret some Ruby for me. I can do my Ruby's things, like say puts hello, and it says hello. I can generate a random number just with the rand keyword, and I get a random number between 0 and 1. Hey, that's exactly what we needed to compute those points. Now, why am I doing this in Ruby? Well, I could do this in any of a half dozen different languages. I think that for just exploring and showing algorithms, Ruby is nice because it gets out of my way with syntax. It almost lets me show people pseudocode that just happens to run. So that's why I'm choosing Ruby for this demo today. We just as easily could do this in Java. In fact, when we get to references for some of these algorithms, I'll show you a website that has it in just about every language imaginable. So we want to be able to get a random point and its distance many, many times. So let's just define a method called distance. And we're going to have it return the distance from that origin 0 on that circle. By the way, I should show you, Wikipedia has an incredible article on pi that has everything you'd ever want to know about it, including some great trivia. The one that cracks me up, let me show you, where's the history of calculating pi. This guy named William Shanks in the 1800s. Well, maybe it's a link off to this. But he calculated pi over the course of 15 years by hand out to 707 digits. But he made a mistake in the 501st digit. So he only gets credit in the history books for 501 digits. Can you imagine doing something by hand for 15 years only to find out you made a mistake 5 years ago that cost you a huge record? Anyway, this is a graphic that comes right off that Pi Wikipedia page with exactly the technique we're talking about here. This is just showing random points landing inside a circle. And you can see the red ones are inside, the blue ones are outside. So we are going to write the code right now to generate that random point. And actually, we don't care so much about the actual point as much as the distance from the 0, 0 point. And I'm going to need 2 points. So let's say random and random. And I want to do the Pythagorean theorem, so I'm going to say math dot square root of random squared plus random squared. And let's say 10 times do puts distance and see what kind of answer we get. Okay, so we get a bunch of points between 0 and that outer point, which is going to be like 1.4 away. In fact, we got one that's outside here, clearly. Remember, these are not the actual points. We threw away the point values. These are just the distance from the origin. So here was 1 here that was outside out of 10. Let's do that again. And here we have 2 that are outside. We can see, of course, random numbers, we're going to get a different result every time. There's 3 outside. There's 2 outside. And it's kind of weird that we're going to use randomness to calculate pi, but it's going to work. So what do we want to do next? We want to, for some large value, let's say 10,000 times. Actually, let's initialize a variable for inside. How many times are we inside? So 10,000 times do. Now, so what did we want to do here? We want to do inside if a random distance is less than 1. So after that runs, we're going to have some value for inside that's going to be however many times we happen to be inside. So let's say inside divided by that 10,000. Now you know what? 10,000 is an integer. I want that to be a float, so we end up doing float math, and we can get some kind of a floating point value. And we're going to multiply this by 4, because remember, we're just doing this on a quarter of the circle. And let's put the value of that and run. 3.1324. That's, for random, that's pretty darn close. I couldn't get that close with a ruler. 3.1396. 3.148. And you know what? With more values, let's use 50,000 points. 3.144. Hey, we got that next digit. Let's see if that's repeatable. 3.14072. 3.13. You know what? I bet if we did more and more, let's do 500,000. We'll get more and more digits. Well, that didn't take long to run at all. What do you say we do that 100 more times? So what are we doing here? 50 million? I won't make you wait for that. I'll use the magic of editing to cut that time. And 50 million times, and we have 3.141. Hey, we're getting pretty accurate. Now, of course, we have all this extra junk on here, and all that little extra junk is going to be a little different every time we run this program. Again, I'll cut. We'll see what that gets to. And after 177 seconds, we have an answer. 3.1416 for 5.9 value. Okay, you know, we're getting more and more digits, but it's taking longer and longer to get those digits. And that is the fatal flaw here in the way this is working, is that to every digit we want to add to this with some kind of certainty, we need to take more and more samples, exponentially growing. So to get any past 10 or 12 digits, this thing is going to take more computer time than I have time to be able to record and get this published today. So it's a useful technique. Actually, it's very useful in a lot of different environments. The technique we're looking at here is called the Monte Carlo method, and it's useful in a lot of computer science and a lot of physical sciences. Anytime we have a set of equations like Pythagorean theorem and the area of a circle, but don't know the value of some physical constant, we can use random data like this, pump through those equations to get some kind of value. And there's a great Wikipedia article on it. This will be in these show notes. Everything that you're going to see today is going to be up on GitHub in a project you can download. And so this is just a broad class of algorithms that are useful for sampling data, running them through some kind of numerical equation, and getting some kind of result out of. And the history of this is pretty fascinating. This was developed at Los Alamos Scientific Laboratory when they were investigating the paths of neutrons through shielding material when coming up with the research into nuclear weapons. And the name Monte Carlo, this is fantastic, although Wikipedia says it needs a citation. This work was secret at the time, and it needed a code name. So they suggested Monte Carlo after the casino in Monaco. And there you'll see this little graphic I was showing you earlier. So that is the Monte Carlo algorithm for calculating pi. And if we were to end there, that would be, a nice little screencast. But we have more. First of all, let me show you what I'm looking at here. This is the code we just wrote, right? I'm going to throw that away, because I have a version here in the library that is a little bit nicer in terms of the fact that we don't have duplicated numbers that we have to change, and it takes a parameter. And I also have a way of running it from the command line. In this project, once you've bundled and have Ruby on your machine and everything like that, I can say rake Monte Carlo. And we get a value, and we can keep doing that, and we get a slightly different value every time. Or I can pass it a parameter. Now, because of my shell, I have to use a backslash to escape these. But let's do that for 50,000 points. And we get another value. This is exactly what we were doing before. Let's do it for 500,000 points. 5 million. And the 50 million, just like we did before. But there are other, more interesting ways of calculating pi. Here's another algorithm you might know, the Leibniz formula. If we take 1 and subtract 1/3, and then add 1/5, and then subtract 1/7, and then add 1/9, we approach that same value of pi over 4. So let's see some code to do that. I should also say that the code we're looking at from here on out is not necessarily mine. I found several great references for pi algorithms, including a website here called Rosetta Code. Here is an example of pi calculated with various algorithms in 45 different languages. And we're going to look at several more Ruby implementations here. But this is also included in the show notes. And here's our Ruby code for the Leibniz algorithm. And again, this was off of one of the references that we'll be seeing. It starts by setting pi to 0. Now there's this number, which is just right now set to 1. It keeps track of whether we're adding or subtracting with this Boolean flag here currently set to true for plus. And then the denominator is currently 1. And if we're plus, then pi, which is currently 0, equals pi plus the numerator over the denominator. So the numerator denominator right now is 1 over 1, 1. So we get our initial value of 1, plus becomes false. Next time through this loop, it goes this path. And we can see this is going to be numerator over denominator, which, because of this denominator equal denominator plus 2, is now going to be over 1/3. So we subtract 1/3. The next time we add 1/5. The next time we subtract 1/7. The next time we add 1/9. Then we subtract 1/11. And after we run for whatever iterations is set to, we multiply it by 4 and return. So I can come over here and I can say rake Leibniz, and it has some default value of like 1,000 iterations. That was a heck of a lot faster than our Monte Carlo version. 3.1413, accurate out to 3 spaces. Let's do that with 10,000. 3.33. Oh, forget the comma. Code's not robust with error and stuff like that. 3.1413. Let's do 100,000. 3.14157. Let's do 1,000,000. 159. Oh, then it goes south. We did 5 million and 50 million before, so let's bump to 5 million. Let's return it fast. And 50 million. Now this is also a nice algorithm that it's running in set time. You know, if whatever 1 million takes, whatever 5 million takes, whatever 50 million takes, is related to however, you know, just the iterations in the math. It's not, you know, an exponential increase. It's n of 1. And but the problem with this algorithm is, again, it approaches values of pi, but the closer we get, we need more and more iterations to get the next value, to get the next digit with any accuracy. And that really slows it down. We can see here it's taking, 15, 20 seconds, and we have pi out to 1, 2, 3, 4, 5, 6, 7, 1, 4, 2, 6, 4, 7 digits. Nice algorithm. I mean, I shouldn't poo-poo it. I've never needed pi out to 7 digits in my life, so it works, and it's understandable. The next algorithm I want to show you is the current world record in terms of speed, and records right now are up to about 12 trillion digits. And talking about the number of digits that we have accurate of pi, here's the article I mentioned earlier. Again, this will be in the show notes, of the chronology of the computation of pi. And it just goes through time and shows how many digits we knew of pi at various times in history. And interestingly, they credit the Great Pyramid of Giza as in 26th century BC as having something to do with pi. That's interesting. We'll talk about that at the very end. That's going to be icing on the cake for this. But so we're computing right now out to 9 digits using that Leibniz formula. And congratulations, we are about 1579 in the history of pi. Today, you can see that, I love this, all records from December 2009 onwards are calculated on home computers with commercially available parts. 6 months ago, October 2014, we have pi out to 13 trillion digits now. That's awesome. Yeah, if you're like me, you kind of stretch your mind at the Pythagorean theorem in the area of the circle, and the minute you see these little sigmas and infinity symbols, and yeah, that's okay. That's math. But I can run down kind of what's happening for you here, what an algorithmic geometric mean is. But this is useful for computing pi, and it's useful because it's simple math, right? It's a very quick algorithm for computing pi. So I have a window here where I can write some more Ruby code. I'm going to say, let's say x equals 5 and y equals 9. And the arithmetic mean of these two things. This is an average. You know how this works. We take 5, we add it to 9, and we divide that by 2. Well, there's something called the geometric mean, which is a similar process, but it's 5 times 9, and it takes the square root. So where this adds and divides, this multiplies in square roots. So let's do a puts on the arithmetic mean and a puts on the geometric mean. And, 5 and 9 average together to be 7, but the geometric mean becomes 6.708, and that's interesting. There's a little gap here. Well, what if we were to define that as a function? Let's say define arithmetic mean to take x and y, and it's just going to return x plus y divided by 2. And let's define our geometric mean to take x and y, and that's going to be math.square root there we go. Okay, 7, 6.7, same answer we had before. Well, what if I were to take the arithmetic mean of the arithmetic mean of x and y and the geometric mean of x and y? I'm averaging those together to get something in between. But what if I were to take the geometric mean of that? See what's going on here? So now they're converging, 6.85. If I keep taking the arithmetic and the geometric mean and computing them together, I'm going to converge on some limit here. Okay, I got my parentheses happy, and this is the last one I'm going to do just as a parlor trick. But now I'm going to show the arithmetic and the geometric mean of these two things again, one more level deep, and we see that they're converging. That's the concept of the arithmetic geometric mean, is iterating through this, and the more we iterate, the more they converge. And we just stop ourselves iterating whenever we've converged on a value that we're happy with. And so that's the notion of an arithmetic geometric mean. And that is used in this equation right here, this AGM function call. And for some reason, for intelligences above my pay grade, that computes out to pi. And of course, there's several implementations of this here. And that's what we're about to see run. Now, we took about 120 seconds to compute out to 5 or 6 digits randomly, and then about 20 seconds to compute out with the Leibniz formula. So let's rake AGM. Whoa. And that just computed, several hundred digits of pi in a second. That's pretty awesome. Let me show you the code. Again, I didn't write this. This was off that website. It uses a library in Ruby called FLT, which is a floating point library for doing arbitrary precision. So with this one, I'm not specifying iterations. I'm specifying the precision that we want to calculate. So we got more digits there. Let's do it a little bit longer. And of course, this is the fatal flaw with all of these algorithms, is that while they're thinking, while they're churning, we see nothing. We sit here and wait. Can you imagine how brave those people are that go calculating pi, where they leave a machine running in the corner of their office for a year, and when they're done, they have 13 trillion digits? I mean, how do you know you just didn't have a typo? How do you know the machine hasn't crashed? Now, my guess is that they build in some redundancy and can have some monitoring to know that's going on. But still, it sure would be nice to have some way of checking our progress. And here we are after a few minutes. This one still hasn't returned, so I've clearly asked for way too many digits than I'm willing to have the patience for while recording this screencast. So let's move on. But wouldn't it be cool if we had an algorithm that actually gave us each digit as it was computed? And I have to tell you, when I saw this next algorithm run, I was blown away. It's called a spigot algorithm. Let's go look at the code. Okay, it's math intensive. And it's got one neat little thing in it in terms of it takes advantage of a feature in the Ruby language about yielding to a block. We can see here it calls this yield n. Every time it computes a digit, it's going to yield to a function we pass in and give us that digit. Let's go see the code that calls this. This generates pi via the Spigot algorithm, and we include the file that we just saw, and we call Spigot. And then we pass it this thing. This is called a Ruby block. And when this code gets called, it's going to be passed a digit. And we're just going to print it to the screen and then flush the screen so we can see it. By the way, I should show you in case you're interested in downloading and playing with this code yourself. Once you have it installed, you can rake -t, and it will give you the 4 different methods that we're showing today and the algorithm, the thing that they take to affect how the run changes. And notice that Spigot doesn't take anything. So let's run this. Wow. I mean, and we're in Ruby. Ruby is often considered a slow language. Can you imagine what this would be doing in C or Java? I'm just really impressed with this algorithm in that, growing up with computers where if I ever saw an algorithm that did this, if they could even handle it, it would, print out a digit every 10 seconds. This just is really impressive to me that while I'm sitting here blathering on, we've probably calculated pi to several thousand digits easily. I let it run for 24 hours and it calculated over 600,000 digits, which is approaching, the world record as of when I was born, which is pretty impressive for me to do in an interpreted language on an afterthought on a laptop computer. I thought that was pretty cool. And that Spigot comes from this paper, which is included again as part of the package that you can download off of GitHub. It shows the algorithm that we're using and goes into about 11 torturous pages trying to explain the math. But the first one of these algorithms that was discovered was bounded. That is, it would stream out the digits, but you had to decide ahead of time how many digits you were going to compute. The unbounded version, you don't have to decide that. It just keeps spewing them out. So I said earlier I was going to end on a note about the pyramids and pi. This guy. This is Sir William Flinders Petrie, and he is considered the father of modern archaeology, as in, pyramids archaeology, not any kind of software archaeology. He is the one that really turned the archaeology into smash and grab. Let's take stuff back and put it on display in the British Museum. To let's sift through the sand and put together the pottery shards and try to figure out these people's lives. And that was a big turning point in archaeology. And he is the first person to get accurate measurements of the pyramids. That is, their base, their height, their width, how level they are, how tightly the blocks fit together, all the stuff that we marvel about today. And when he had these numbers and people started crunching the numbers, they found that if you took the base of the pyramid, the area of the base of the pyramid, and divided it by its height, you would get a number that very closely approximates pi. And people looked at this like, wow, we had no idea that the ancient Egyptians had any idea, any notion of the value of pi. And of course that fueled conspiracy theorists, and aliens helped build the pyramids, and of course one of my favorite sci-fi series, the Stargate stuff. But, it turns out it's a much simpler explanation than that. And we really have a lot of evidence about how the pyramids were built, more than most people realize. And of course, the pyramids just didn't appear out of thin air. We have, archaeological evidence of the experiments that they built to build the pyramids. We have step pyramids that were smaller and showed examples of different kinds of construction. And in particular, here's one where they were playing around with the height, the kind of the slope of the pyramid. It's called the bent pyramid. They started building up at a certain angle, and as the weight of the pyramid started crushing the corners that they would break apart, they said, we better change that angle. And halfway through construction, they just changed the inclination of that pyramid. It's called the bent pyramid. It's still around today. You can go and take a tour of it. And so we can see that they were playing around with different kinds of construction techniques. And of course, there's the Great Pyramid of Giza. It's one of those three famous pyramids on the Giza Plateau. And if you take the base, the length of the pyramid, so the length squared area, and divide it by the height, you get something like 3.1416, right? It's remarkably close. And the reason that is because through trial and error as they were building the pyramids, they realized that if they wanted to build a pyramid that didn't collapse under its own weight, they would take a measuring device that was based on a wheel. Let's say, they had a measurement of a cubit. It was equivalent to something like 1.4 feet. But let's say you wanted to build a pyramid 100 cubits high. You took a wheel that was a cubit in diameter and rolled out the base. I'm sure you've seen those surveying devices that look like a wheel that you walk along with. And they let the wheel rotate 100 times. 100 times rotation on the wheel, 100 cubits high of a wheel that's a cubit in diameter, and the pyramid wouldn't fall. And just by virtue of the fact that they were using a circle in the measuring device and a multiple of the number, 100 this, 100 that, pi was encoded in the dimensions of the pyramid. And just a neat little pyramid fact about pi to celebrate your Pi Day. Well, happy Pi Day, everybody. I hope you found some interesting stuff in this talk. And if you've listened this long, thanks for paying attention. I know I love to ramble. I hope I can tighten this up a bit in editing. Thank you.
2828648299375106286421177067823086408230664709384